Let's consider some group actions that apply to all groups. In this case, our group is going to act on the set given by the group itself or a coset space of our group by some subgroup H. Now, let's recall what a group action is. So if we have a group acting on a set X, so G on X, for each element of the group, we're going to have a pi of G, which is just going to be a map from X to itself, satisfying the following two conditions. Pi, the identity, is going to send X to X for all elements in our set. Pi of G times H on X is going to be equal to pi of G on pi of H on X. So the first statement says pi of the identity is equal to the identity map on X. Second statement says pi is going to respect the group multiplication. We saw last time, another way to say this is that we have a homomorphism pi going from the group into the group of bijections from X to itself. Now, for what we have in mind here, we'll call this the left regular action G on the group itself. So the way we define this, pi of G on X, here X is also an element of the group, just given by taking G times X. Now, to show that we have an action, if we apply pi to the identity to X, we take E times X, which is just X, so the first condition holds. For the second condition, we take pi of GH on X, so that's GHX. Then H times X is just pi of H on X. Then we have the G out in front, which just turns into a pi G. So we have group action 1 and 2. Now, since we have a group action, it follows immediately that each pi G is going to be a bijection. If you're not doing group actions in your course, we could just show this straight away. So let's do that. Not a lot of work. So to show 1 to 1, okay, I'm going to assume we have some pi of G. So we fix G, and we'll assume that pi G on X equals pi of G on Y. To show 1 to 1, I want to show that X is equal to Y. If we write out the definition, we have Gx equals Gy. We can cancel, and we have X equals Y, so 1 to 1. For onto, I have to show that pi of G sends some element to any X that's in the group. So if I apply pi of G to G inverse of X, then we get G inverse X, the G's cancel, and I'm left with X. So we have onto also. So bijection. Now, in the language of group actions, the left regular action is transitive. So this means if we take any 2 points in our set, say X and Y, there's going to be some element in the group G, such that pi of G carries X to Y. So if I take any 2 points, I can get from one point to the other by picking the right group element. Now in our case, if I want to go from X to Y, I just apply YX inverse. Then the X's go away and we're left with Y. Now, in terms of the partition that comes with the group action, this isn't very interesting. We have only one orbit. In addition to the left regular action, we have the right regular action. So here, everything's going to go through as before. The only difference, pi of G on X is going to be equal to X G inverse. The reason we need the inverse when we act in the right is because of the inverse rule for a product. So if I take the inverse of a product, we switch the order, put inverses on each term. So let's check property 2. If we apply GH to X, then I have GH inverse on the right. We use our product rule, so I have H inverse G inverse, and then note how we pull it apart. I have a G inverse on the outside, so I'm going to say that this is pi G applied to X H inverse. Then our inside term is just going to be pi of H applied to X. So when we pull things apart correctly, I need the inverse to get property 2 to work out. Now, considering the right action doesn't give us any more information. I could pass from the left action to the right action and back by considering this map given by taking the inverse. So what happens is, if we apply the left action, take inverses, it's going to be the same as if we took inverses and then applied the right action. So I could push from one side to the other using this map. So no new information. Now, for an example, let's consider G equal to Z mod 3 under addition. So we're going to have a map for each group element. So pi 0, pi 1, and pi 2. Pi 0 is going to be the identity map. Okay, that would be the same as adding 0 to each element, so that checks out. If I add 1 to each element, we get 0, 1, 2 going to 1, 2, 0. Bijection, that checks what we expect. And for pi 2, we have 0, 1, 2 going to 2, 0, 1. So again, a bijection. We also note pi 0 is not equal to pi 1, is not equal to pi 2, is not equal to pi 0. So we're getting all different maps when I consider different group elements. That's going to be a feature of regular actions. What does the left regular action get us? It gets us Cayley's theorem. So the idea is going to be, if I want to understand groups, we try to contain these groups in other groups that are well understood. So the groups we're going to use here to contain all groups are going to be the symmetric groups. Cayley's theorem says, every group G is isomorphic to a subgroup of the group of bijections from G to G. If G is finite, this just says G is isomorphic to a subgroup of symmetric group on n letters, where n is the order of the group. So when G is finite, we're always going to be able to put it into a symmetric group if the size is large enough. Now, we already have that the left regular action is going to be a homomorphism from our group to the bijections from the group to itself. So we just want to show that pi sub L is 1 to 1. And then we're just sending G in to the bijections as a subgroup. To show 1 to 1, if we have a homomorphism, we just need to show that the kernel is the identity. Now recall, the kernel is going to be the set of all elements in the group such that the left action of that element is the identity map. So what do we show? We're just going to suppose we have pi of G on X equal to X for all X in the group. So that's saying that we have the identity map. That says G of X is equal to X for all X in the group. We use cancellation, and then we have that G is the identity. So that shows that the kernel has only one element in it, the identity. Our proof actually says something much stronger. Okay, note here, I don't need this for all X in G. If it happens for just one X in G, we cancel, we get the identity. So that means when we're using the left action, there are no fixed points unless you're using the identity itself. When we consider specific examples, the symmetric group that comes from Cayley's theorem is usually going to be too large, but not always. If we consider Z mod P with P prime, the order of our group is equal to P, so Cayley's theorem says we can embed Z mod P into S sub P. S sub P has P factorial elements, so there's a lot of room for that Z mod P, but we can't embed Z mod P into any smaller symmetric group. Now, see that if we have a permutation of order P, it's going to be a product of P cycles, and the first symmetric group where we have P cycles with P prime is going to be S sub P. Now, for comparison, let's consider Z mod 30. Cayley's theorem says we'll be able to embed Z mod 30 into S sub 30, but we can do better than that. We can embed Z mod 30 into S10. So all I have to do is find a permutation that has order 30 in S10. The way I get that, I'm going to take the 2 cycle 1, 2, the 3 cycle 3, 4, 5, 5 cycle 6, 7, 8, 9, 10. So this has order 2, order 3, order 5, and these are disjoint, so it's like they behave independently. So if we start raising the powers, the only way that we get all 3 of these to line up equal to the identity is going to be when we hit the 30th power. So order 30. Now, the question becomes, how do we adapt Cayley's theorem so that we get a smaller symmetric group? Instead of using the group G for our set, we can instead try G mod H, okay, the left coset space, where H is some subgroup in G. We'll call this the left regular action of G on the left coset space, G mod H. And our definitions are going to be as before, except now instead of acting on points in the group, we're acting on left cosets. So pi of G is going to carry G mod H to itself. Pi of G on the left coset XH is just GXH. We have the 2 properties for the group action. They're straightforward to show. We have that pi of G is a bijection from G mod H to itself. And we have that pi is a homomorphism from G into the group of bijections from G mod H to itself. What we're not guaranteed is that pi is 1 to 1. So there might be a kernel here now. Before we consider an example where it fails, let's first check one where it works. So we'll consider D sub 8, symmetry group of the square. By Cayley, we can embed D sub 8 in S8. So S sub 8 has 8 factorial elements. But we note, if we just consider the labels, okay, D sub 8 sits inside of S4. Can't do any better than that because the order of S3 is equal to 6. Now, if I consider H equal to the identity and 2 cycle 1, 3, the left coset space has 4 elements. So if I can show that the kernel of pi is the identity, we have 1 to 1, and I can embed D sub 8 into S4 as expected. So let's suppose I have some G in the kernel of pi. So that says pi of G on XH is equal to XH for all X in the group. So here I just have the identity map. That says GXH equals XH for all X in the group. If I push this X to the other side, we have X inverse GXH equals H. And if these 2 cosets are the same, we have the identity coset here. That means X inverse GX is an element of H. Now, if I let X be equal to the identity, because we're letting this be any element in the group, that says our G has to be an H. So we've narrowed it down to 2 elements. If G is equal to 1, 3, well, I can just conjugate by 1, 2, and we notice we get 2, 3, and that's not an H. So that means 1, 3 is not going to be in this kernel. So that means the only thing in here is the identity, and this map is now going to be an embedding. It'll be 1 to 1. For an example with a non-trivial kernel, let G be equal to S3, symmetry group of an equilateral triangle. I'll let H be the rotation subgroup. So we have 2 cosets. If we reason as on the previous board, the kernel of pi is equal to H itself. Now, that says pi is not 1 to 1, but we could see that directly. So pi is going to carry S3 to S2, and if we count, we have 6 elements here, 2 elements here, so not 1 to 1. Now, going back to the previous board, we can make a precise statement about the kernel of pi. Now, this is going to depend on the subgroup H that we choose. For the previous board, we have this statement from manipulating cosets. If we translate what this says, the kernel of pi, okay, it's a normal subgroup because it's a kernel. It's going to be the largest normal subgroup of G contained in H. So, if K is a normal subgroup of G, K is contained in H, then K is contained in the kernel of pi. For an example, we had the dihedral group with 8 elements, the symmetries of the square. We had the subgroup H equal to the identity and the 2-cycle 1, 3. This is not a normal subgroup. The only normal subgroup that it contains is the identity element. So we had that the kernel there was equal to the identity, and we had 1 to 1. Now, this suggests a recipe for getting embeddings into small symmetric groups. What we want to do is, we want to look for large subgroups H that contain only the identity subgroup as a normal subgroup in G. Now, if we try to arrange it so that G has no normal subgroups, but the identity and G itself, we call that kind of group simple. We've only seen one class of simple groups so far, when they're abelian. In that case, the group that's abelian and simple is isomorphic to Z mod P, where P is a prime. Now, if we have an abelian group, every subgroup is normal. So if I arrange for P to be a prime, that's the only way we can have no subgroups other than the identity in the group itself. For non-abelian simple groups, we haven't seen any of these yet. We'll say more about them in the next talk. We won't come up to the first one until we have the order of the group equal to 60. So that's going to happen by just checking for normal subgroups in 1 through 59. When we get to 60, it's possible to have non-abelian and simple. Now, one isomorphism class is going to be given by A5, alternating group on 5 letters, which we'll talk about next time. One question becomes, okay, A5 is going to be the only isomorphism class for non-abelian and simple of order 60. So the way that we see this, what we'd do is, if I have non-abelian and simple of order 60, we look for a subgroup isomorphic to A4, which has 12 elements. That'll give us an embedding into S5, and then we note the only subgroup of order 60 in S5 is A5. So if we try to have anything else, we have to wind up going to the A5. Here's a corollary to our main result. If G contains a subgroup H such that the order of G does not divide the index of H and G factorial, then H contains a non-trivial normal subgroup of G. Now, what's this really saying? So how do I translate this? The index of H and G is the number of cosets. We put a factorial on here, and that's going to be the order of the symmetric group. So what we're doing is permuting the cosets around. If G, okay, the order, does not divide this number, then I cannot embed G into this symmetric group. So that means the kernel of pi is non-trivial. The kernel of pi is going to be the normal subgroup that satisfies these conditions here. Now, an application of this, if P is prime, if the order of G is equal to P squared, then G is an abelian group. And in turn, G is isomorphic to either Z mod P squared or Z mod P cross Z mod P. Now, we'll see a nicer proof of this later on, but here goes. By Lagrange's theorem, the order of elements in our group are either 1, P, or P squared. They have to divide the order of the group. If we have an element of order P squared, then our group is cyclic. It's isomorphic to Z mod P squared. So let's assume that that case doesn't happen. That means we have only elements of order 1 or P. The only element that can have order 1 is the identity. So we have another element of order P. So let's call that X. I'm going to take the group generated by X, so that's cyclic of order P, call that H. Then we note, with this condition here, we have the order of G is P squared. The index of H in G factorial is P factorial. And P squared does not divide P factorial when P is prime. So we have that P divides P factorial but the remaining p will not divide any of the remaining factors. So that means H is going to contain a non-trivial normal subgroup in G. Only subgroups of H are going to be either the identity or H itself. Non-trivial means we have to have H itself normal in G. Now, let's pick some Y that's not in H. Because the identity element is in H, Y has order P. If I consider, okay, we're going to conjugate X by Y. So here we're using the philosophy behind semi-direct products. Because H is normal, that means we're going to have an automorphism coming from this conjugation. So we're going to have some pi in the automorphism group of H, and here we have pi applied to X. Now, aut of H, okay, H is cyclic of order P, so aut of H is isomorphic to Z mod P star. That's a cyclic group of order P minus 1. Y has order P, so that means the order of this automorphism is going to have to divide P. Now, because we have that P minus 1 and P are relatively prime, only way that pi can have order P is if it's the identity. So that means yxy inverse is equal to x, or yx equals xy. Now, if I consider all powers of x times all powers of y, I can get a subgroup isomorphic to Z mod P cross Z mod P in our group. But since this has order P squared, that's going to be all of our group. So that's our result.